What the proposition is saying, we write the series as a power series in the last variable, with coefficients in the Tate algebra in the first variables. The proposition says that, under the assumption that the whole series has Gauss norm equal to 1, being distinguished of order S is exactly the same as saying that, after reduction modulo the maximal ideal, the series becomes a polynomial of degree exactly S in the last variable, and its leading coefficient becomes a non-zero constant in the residue field. So the point is that the distinguished property can be detected just by looking at the reduction. First direction. Order S. By definition, this means three things. The coefficient of order S is a unit, its norm is equal to the norm of the whole series. And every coefficient of higher order has strictly smaller norm. Since the norm of the whole series is 1, the coefficient of order S also has norm 1. Why its reduction is a non-zero constant. The coefficient of order S is a unit in the smaller Tate algebra. Now we use the unit criterion for Tate algebras. An element is invertible if and only if its reduction is invertible in the polynomial ring over the residue field. So the reduction of that coefficient is invertible in the polynomial ring. But in a polynomial ring over a field, the only invertible elements are the non-zero constants. A polynomial of positive degree cannot have a polynomial inverse because degrees add under multiplication, so the product could never be equal to 1. Therefore, the reduction of the coefficient of order S must be a non-zero constant. Why all higher coefficients disappear after reduction? Since the series is distinguished, every coefficient of order strictly bigger than S has norm strictly smaller than the norm of the coefficient of order S, but that norm is 1. So every higher coefficient has norm strictly smaller than 1. Now we use the basic reduction criterion. An element reduces to 0 exactly when its norm is strictly smaller than 1. Hence all coefficients of order bigger than S become 0 after reduction. Conclusion of the first direction. So, after reduction, only the terms up to order S remain, and the coefficient of order S is a non-zero constant. That is exactly the desired form. Second direction. Now assume that, after reduction, the series becomes a polynomial of degree exactly S, and its coefficient of degree S is a non-zero constant. We must prove that the original series is distinguished of order S, so we need to check the three conditions in the definition. Why the coefficient of order S has norm 1, its reduction is non-zero. That means the original coefficient does not lie in the maximal ideal. And not lying in the maximal ideal means that its norm is not strictly smaller than 1. On the other hand, the whole series has norm 1, so no coefficient can have norm bigger than 1. Therefore, the coefficient of order S must have norm exactly 1. Since the whole series also has norm 1, its norm is equal to the norm of the whole series. Why the coefficient of order S is a unit, its reduction is not only non-zero, but actually a non-zero constant. Now we use again the unit criterion for the Tate algebra. If the reduction is invertible in the polynomial ring, then the original element is invertible in the Tate algebra. A non-zero constant is invertible in the polynomial ring, so the coefficient of order S is a unit. Why all higher coefficients have strictly smaller norm? The reduction has degree exactly S, so all coefficients of higher degree reduce to 0. By the reduction criterion, if an element reduces to 0, then its norm is strictly smaller than 1. But the coefficient of order S has norm 1. So every higher coefficient has strictly smaller norm than the coefficient of order S.